topic today is flow assurance considerations in hydrocarbon field development and planning. And the main intention of this lecture is not to make you experts in flow assurance. For that, there are many other courses and lectures that you can watch and material that you can refer to, but simply how that we are aware of what kind of flow assurance issues we have to consider when planning and designing the field and what consequences do they have on the field planning process. So this is an overview slide showing some of the issues we might have. This slide I took it from is adapted from a presentation by Equinor, which I thought was very nice. So we have, for example, we have here the different regions where we are in the reservoir, upstream well, a bit more downstream pipelines and flow lines, and then we have process. And we have where these issues typically affect in which region. Okay? And offshore fields, most of offshore fields, they have strong subsea components, especially in Norway. There are some fields like they have dry Christmas trees, like what we have discussed before. So they behave mostly like onshore fields. Okay, so you don't have this part. Many of the issues that affect this part, the flow line and pipeline, they are not affecting in systems where I have dry Christmas trees. Okay? But most fields, especially in the Norwegian continental shelf, they have a strong subsea component, and then we should look also into those. Okay, so we have asphaltenes, we have scale affecting the whole chain, we have hydrates mainly affecting a bit the well, but mostly the flow lines and pipelines. Wax also affecting mostly pipelines and flow lines. Emulsion affect almost the whole range. FIV stands for flow induced vibration. Corrosion affects the whole range. You have slugging, erosion, naphthenates, foam, and also I put it a bit out here, but it's microorganism growth, okay, which is a big issue usually topside. So my intention here is to simply go at least through a few of them, so we have like a very brief or we have some understanding of what they are, and and then we see how that affects the design or the planning of the field. Okay, so hydrates is a structure like shown here in the upper corner, is where you have the water molecule and it forms some sort of a structure, okay, that it houses small molecules, size molecules, like for example, in this case, methane. Yeah, and if they are formed, we are going to see later, but they are formed in at a particular conditions of pressure and temperature. But it's essentially this structure, a solid structure that houses molecules that are of a relatively small size, okay, a few Armstrongs in size. You see here what kind of issues can cause. You have a block of hydrate on the pipe, and here you have exactly the deformation process. A video from DTU, Denmark Technical University, and you should see here how the hydrate particles are forming. Okay, so some of the conditions of formation of hydrate is that you need to have first water, because this this solid structure, this crystal, is made out of water molecules that are aligned in a certain way due to the hydrogen bond. And then you have small hydrocarbon molecules, especially methane. You have methane hydrate, but you can also have hydrate of CO2, for example. And you have also a particular range of pressure and temperature. In a very simplistic way, if we make in our pressure and temperature, like that, the hydrate equilibrium line is something like this for high pressures and relatively low temperatures, okay? Or you want also to have for very low temperatures, you have relatively lower pressures, okay? And all the area that is to the right, it's where you don't have any risk of hydrate, and where you have to the left, you have formation of a hydrate. Okay, and if we put here to the right, I'm showing now the same pressure and temperature diagram. I'm putting the phase envelope of the fluid that we have on the pipe, and we have the inlet of the pipe, which is 1, and I'm flowing towards the outlet of the pipe, which is 2. So what happens typically in flow lines and pipelines when I'm transporting the fluid from a high pressure to a low pressure, let's say the separator facilities in this case, okay, the temperature is going to be reduced. Usually the environment is at a lower temperature than the fluid, so then I have heat transfer, the fluid loses energy, heat to the environment. So at some point it might happen that it crosses, here I have my original hydrate line, and at that point I will have hydrate formation. And hydrate is not something I can live with it, but it's something that potentially could block the pipe, okay, if left unaddressed. So one approach you see here, you have other lines, okay, that they alter this equilibrium line of hydrate by adding what is called a hydrate inhibitor, okay, in this case methanol. Okay, and if you add 30% weight, that's on the water. That means that the liquid phase, the free liquid phase, has 30% methanol, and then the is pushed quite a lot to the left. And then you have to choose an injection and amount of methanol, considering the amount of water you have, such that at the exit of the pipe you don't have any risk of hydrate formation. Very quickly, wax basically are these also um, um, large alkanes, paraffins molecules, 618 to 636, and they're alkanes, they are like long chains. Okay, and they form also these plugs. Okay, they accumulate on the wall, and they can also cause plugging. Okay. The main difference between wax and hydrate is that this process occurs gradually. So you have an accumulation, it's like when you have accumulation of fat on the arteries, and that causes that they will become, the cross-section area will become smaller and smaller. So it's not something that suddenly plugs the pipe, but it's something that is more gradual. Okay, here you have a diagram. It's mainly, we're going to see just now a diagram, but essentially if you paint it in pressure and temperature, you see that you have a region for low temperatures that essentially you have wax, okay, where these wax particles come out of solution. Okay, that's an experiment where I'm measuring the oil viscosity, and I reduce the temperature. So in this region you simply reduce the temperature and the viscosity is increasing. At some point you have what is called the the cloud point, okay, or also called the watt, which is the wax appearance temperature. And that's where these wax crystals, they start to precipitate from the oil. It has an oil we are measuring its viscosity. And of course, after that point, you have an increase in viscosity on this direction due to, one of them is due to the temperature, simply the viscosity is increasing when I reduce the temperature, but also you have these wax particles that are causing the rheology of the fluid to change. Okay, it's like you have a drilling mud that you start to add solids to this drilling mud, and it behaves in a, for example, can behave in a non-Newtonian way. So in this case, in this region, you have a change that can be quite difficult to move this fluid because it exhibits a non-Newtonian, it exhibits often a non-Newtonian behavior. So then you reach another point in which you have, that's called a pour point, okay, in which it becomes extremely difficult or impossible to flow normally. So if you have, the analogy is if you have on a glass, you have this oil, so then you try to pour it and it will be fairly solid or very difficult. It will take long time to to move. Okay. So the mechanism of wax here I'm showing is the concentration of wax particle if we are going to measure on weight percent. Okay, so it's the weight of wax particles, okay, over the total weight, okay, times 100. And you see that when you reduce, initially you have no wax particles, but then when you reduce the temperature, you're starting to come out. This is, in this case, this is a watt, okay, before you didn't have any wax, okay. And after you start reducing it below the watt, okay, in this case it's 39, then you start getting more and more particles until they take up, in this case, at minus 50, they take up around 11%, okay, of the total weight of the mixture. So that's one type of experiment is done on wax. And one thing that happens with wax is that if we see the cross section of the pipe, you have the temperature typically, the temperature, if we are going to plot the temperature, okay, along the radius, okay, of the pipe, we usually have a high temperature, okay, and it's starting to reduce until we reach the wall, okay, and then it continues to reduce. So if, let's say, the fluid, okay, it's below the wax appearance temperature, the concentration of wax particles here is going to close to the wall, which is the coldest, okay, is going to here is going to increase. Okay, so the concentration, this concentration is going to increase, while here, because the temperature is slightly higher, it will be lower. Okay, so that causes a gradient of concentration. Also, if I plot the concentration of wax particles, this C has the inverse concentration, right? It has concentration profile. Okay, C will be something like that, where you have high concentration of particles here and low concentration here. So it's that difference in concentration, but in the liquid is exactly the opposite. In the liquid, I have less particles, less wax that is dissolved in the fluid. Okay, so I create essentially a travel or a migration of wax particles or of wax components, okay, or wax molecules to the wall. Okay. So essentially, and the wax that starts precipitate, you have some mechanism how it adheres to the wall. Okay, the wax that is coming out of solution, it starts to stick to the wall, and we're not going to talk about that mechanism, but actually has a physical mechanism how it gets attached to the wall. So wax is not only enough that it precipitates, but also has to have a cold wall. Okay. In this case, the pipe has to be cold, and then I have to have this because otherwise, if this all this wax come out of solution, then I won't have any problem because then the fluid won't have any more wax to give to precipitate. Okay, but in this case, we create a concentration differential, and then I have migration of wax molecules dissolved on the liquid that they are going to migrate towards the wall. Okay, so that's essentially what this N is saying, is that you have a mass transfer of wax molecules to the wall. Okay? And one way to express that transfer, okay, is essentially is this guy that I told you before, okay, the differential of concentration with radius, okay, that you have um, okay, that you have more in the wall that you have on the core of the fluid. Okay, that's the core of the fluid. But also, if we then use the chain rule, okay, we have dc dt. That's something that we measure in the lab. Okay, we know exactly the expression, and here we have used a straight line, and then we need this part, okay, dt dr. that we know how to calculate if we have, for example, different layers. Okay, we have convection, we have conduction, we have external conduction. So this guy, we know how to, we know how it behaves. Okay, you have the core of the fluid, you have boundary layer, you have the changes of temperature in the fluid on the radial direction. So that's an example of a simulation where you have along the pipe on the x-axis, okay, that can be meters or kilometers. So you have how the temperature is decreasing along the pipeline, and then you have at some point you reach the wax appearance temperature, okay, and then with time, that simulation tells you time 10, you have and some accumulation, some millimeters of wax on that wall, and then it's getting smaller. Okay, the reason why it's getting smaller, it's the temperature of the fluid also starts to reduce. Okay, the heat transfer with the environment, it becoming less and less, so the fluid doesn't cool down as much as in this location where you still have a relatively warm fluid. Okay, in our case that would be 39. Okay, and with time you have 10 days, and then you go to 60, then you go to 120, that if you do nothing, then the thickness of that wax layer is going to become thicker and thicker. Okay, that will become a problem and eventually plug the pipe. Okay, so that's the wax profile that I think we have calculated in an exercise some previous years, where you essentially use that equation to calculate what is the transfer of wax to the wall, okay, with that equation, and then you simply use the dTdr, okay, that is going to be changing for each location. Okay, it will be less and less as the temperature is going down. Okay, let's say that the temperature, we can put here the temperature of the ambient, for example. Yeah, and what's driving the process is essentially this. What defines the dTdr is basically that difference. Okay. Okay, asphaltenes, they are a bit from the same family of wax, but quite different. So it's also some solid tar-like substance like asphalt on the street, but instead of being made by long alkane chains, is made by this type of components. Okay, cyclic, that have oxygen, have nitrogen, have sulfur, okay, and are cyclic hydrocarbon, and quite heavy with a very high molecular weight. And of course they make is much more like a crystal-like structure, much harder than wax. And here we see they caused by a few mechanisms we're going to discuss on our summary table later. But essentially, if you add a light component, okay, like lighter alkane or lighter some paraffin, some gas, it affects the solubility of this component in the oil. Okay, and then it precipitates. Also, it can be naturally existing on the oil, like if you have a heavy oil in tar sands, they have these components naturally occurring, okay, and they attach to the wall, usually to imperfections. There is always a component of how they attach to the wall. There is some effect of the interfacial properties they can attach to the surface. Can you see the area here where this the area where this shaded is where these occur, and essentially when I'm reducing pressure also can happen if I reduce pressure. Here I'm saying that's the production path from the well to the separator. So here the light components are expanding in the mixture, okay, in the solution, in the oil. So they occupy, it's like they were occupying more space. So it means that they're increasing in a way is quantity. So that causes these guys to precipitate. Okay. And also essentially disappears because at some point all of these light components essentially go to the gas, and then the oil becomes again heavier, okay, with the heavy components. Scale, deposition of these minerals, of these salts, okay, on all kind of components, and scale it deposits on these imperfections that we have. Either we have grooves, we have path, we have valves that they deposit on, and typically this is barium sulfate, calcium carbonate, and even salt, regular salt. And we have different mechanisms for scale to occur. Again, this is not like asphaltenes and wax. This is not something that is going to block from one day to another, but it's also something that takes time. It's an accumulation process that happens with time. But basically, you have two mechanisms, or the most common are when you have, for example, formation water that is rich in these minerals, but it's on these components, and you mix it, for example, with injection seawater, okay, that is rich in SO4. Then you join these two, and then boom, you have this scale, okay, this salt. Also, one other process you have if that with CO2 to form it, when pressure goes down or temperature goes up, then these carbonates they tend to dissociate, and then they tend to join with calcium. Okay, those two different types of scale. Erosion, we refer to the loss of material, okay, of solids, of components, of pipes. Okay, in this case we have a choke. I don't think we have discussed choke, but essentially this is a cage choke where the fluid flows around this choke and then enters through the holes, and then they, because essentially you have, if you see it from the top, you have a stream jet hitting on both sides. So they hit each other in the center and then continues to flow down. Okay? So in this case, it's erosion that actually affects the integrity of the choke and lets it, and it doesn't operate normal anymore. And here you have a manifold where you might have, because of the change in direction of the fluid, you have some areas where you have high velocity, and then you can create also some erosion. Okay, erosion, you need to have a solid particle or some sort of particle on the fluid, and typically is sand due to sand production. Okay, high velocities together with sand production, that the particles are hitting the wall uh, repeatedly, and then you cause this loss of material. Slugging is intermittent flow of liquid and gas on a pipe caused on different flow lines, well or pipeline. So here we see one example that's produced by a student of Professor Ole Jørgen Nidal, who is a professor in multi-phase flow. Okay, and essentially here you're not producing anything, simply zero production. Yeah, and that process has been is slowed down significantly, so we can see what happens, but in the reality it can happen much quicker. Okay, so if you plot, let's let it go, the rest. Okay, so if you plot here, we plot the Q of liquid with time. Okay, we're going to get simply, we didn't get, let me change the color. Okay, we don't get anything, and then we get a peak with a big block. Then we don't get anything, and then we get another peak. Okay, in a kind of in a simplistic way. So essentially that is, you get a batch of liquid. Okay, and that can be an issue for the downstream process. That is, remember, all of our topside process, all of our downstream process is usually designed for steady state operating conditions. Okay? Like for example, in this, if we consider a vertical separator, and we have a valve here, a control valve, Okay, and remember we have a floater, we have some other liquid level, and then that's affecting that valve. So we have different levels in this separator. Okay, we have normal liquid level, we have low alarm level, then we have low alarm, low, low. Okay, or level alarm, low, low. Okay, so if the at this level alarm level, you will get a warning. The operator will get a warning that you have reached that number, you have reached that value, and that you have to do something. And if it doesn't do anything, then in this, usually in this level alarm low low, then simply you have a shutdown. Okay, and the same thing when it's high, you have level alarm high and level alarm high high. So when the point is that when you get a slug, okay, let me change again the color. Okay, typically you have some room for the slug if something happens. Okay, you have some distance or some volume in between their normal liquid level. Okay, and this will be your buffer for slug handling. Okay. But as you can see, it can be relatively small, that volume. So you can take slugs of relatively moderate to small size, but if you're going to have big slugs, then that can be an issue because if you receive that uh, continuously, okay, remember that at this point you're going to shut down the system. Essentially, you're sending the signal to shut down this valve, to close the process. And then to restart the process is a long task that you have to invest a lot of hours, and in the meantime you're wasting production. Okay, and it's not enough because it takes some time depending on the slug that you're receiving here. Okay, here we say QL versus time. Again, we're saying that you receive a big batch suddenly, okay, with time, and you don't have enough time for this valve to act in principle and then take all of that fluid out. Mhm. The same thing here, we have another example if you have a horizontal separator, okay, and the main risk there is if you go above this level, okay, then you're going to get significant entrainment of liquid on the gas line, okay. Um, Here is a video. So what we do in case we know we need to handle the slugs, and this is typical in pipelines that have gas and liquid. Okay, you use this type of separator, which are called a slug catcher, and here the inlet is on this side below, and you have a distribution manifold that goes through several pipes. Okay, and here you have liquid, and you see how the slugs come and they accumulate. These are inclined. I'm not sure if you can see very well there, but it's actually inclined in this direction. So it's reducing the elevation along the pipe. Yeah, and this because of the big volume it has, it can absorb these variations in that you get in inlet liquid. The main problem is that you cannot have this on a vessel. So if you have to have slugs, you have to find and you have a vessel, you have to find another way to to handle them. This can be built only on a kind of land facility. Okay, another problem we have corrosion. This electrochemical reaction when I have that I lose material in one part of the material, yeah, one part of one area location, and then I gain on another, and that can cause a lot of issues with integrity. You see here a part of a casing that has pitting. Okay, and you have another part where you have the growth of material, and it actually is the contact of the metal with water. Okay, and you have another typical issue when you have transportation of gas, for example, with water that is either free or condensing from the gas, that you can have this corrosion. Okay, you can have this is called top of line corrosion. emulsions if we have, for example, as if you take a bottle and you have water and you have this is water, okay, even if it doesn't look like water and oil, and then you mix them vigorously. That's what happens when it goes through valves, when it goes through the choke, when it goes through a manifold. It has to change direction multiple times and then it gets mixed. So then you can end up with something that is like a fine unstable dispersion. Okay, if we look at it, we still see some in case particles of oil. Okay, if we are saying it's a dispersion, fine dispersion of oil in water. Okay, very fine and very stable. And we have the matrix is water. Okay, you can have also all kind of crazy things where you have dispersion of water also in oil, or you can have multiple dispersions, one inside the other. Okay, but essentially the definition of an emulsion is that it becomes quite stable. So to separate, it will take significant time. Okay, and it's also the sizes are very small. And one of the problems we have for separation that's important, if this mixture, emulsified mixture, reaches the separator, then remember separators typically have retention time in the order of minutes. Okay, we're saying maybe 3 to 5 minutes. But if you take to separate this a few fraction of an hour or hour, then it's not something that you will be able. You will need a much bigger volume. Okay, so you won't be able to separate it. Another issue it has is that this emulsion, if here I'm plotting the viscosity of the mixture of that emulsion, okay, with the amount of water it has. So this will be 100% water, this will be 100% oil, and when I increase the amount of water, okay, simply have a behavior which it's here I have a water in oil dispersion in a matrix, and then I have that it's increasing, okay, until I reach an inversion point, okay, and then it starts to decrease. And that inversion point can have, you see here the change. The oil had a viscosity of 80 centipoise, but when I add water, simply I get a viscosity of it's almost like 10 times more. Okay, 8 to 7 times more, let's say, which is a big problem for transporting this fluid in the flow lines. And after that I have this sudden drop. So remember in the field, in the life of the field, when I have the water cut and I have time, okay, the water cut typically I don't have much, but then it starts to increase, okay. So I'm going to pass probably 90% I have here, and I'm going to cross at some point. I'm going to, if I have some problem with emulsion, I'm going to experience this issue on my field. Foam, okay, when the gas becomes trapped in small uh, cover by oil, by the liquid. Again, it's also a big issue to separate this foam and also triggers the level control of the separator. So here we have a summary table, and I hope you don't get too bored by looking at this table, but we have first um, hydrate. The cause of hydrate we have discussed before can cause sudden blockage, and one of the measures we have are to reduce the hydrate formation region that we have seen before. Simply you do continuous or you do on-demand injection of chemical inhibitor. Okay, maybe the pipeline during regular conditions is outside of the hydrate region, but when I shut down production, okay, I'm letting the fluid be stagnated and it's going to cool down, and I might have the formation of a hydrate plug, okay, that is going to plug the pipe. So in that case, I might want to inject some inhibitor before I shut down production. Okay. Other mechanisms are to restrict, you remember the T and P along the pipe, they go inside the danger region, So some measures are to avoid that they are going inside. So one thing is to avoid that they lose too much temperature. That means improving the thermal insulation. You are giving energy to the fluid also to compensate for what is lost to the environment. And then you have electric heating and other solutions. You also have some chemicals that they try to mess with the kinetics of the hydro formation, okay? Because you can have crystals, but then they start to agglomerate, and that's when it causes the blockage of the pipe. But these are not such traditional measures. Then you have others that I put here in red because they haven't been tested on the field. But you have cold flow that you try to this agglomeration process. You try to avoid it, okay, somehow. And water removal and gas dehydration. If I take out the whole water from the stream, then I won't have any hydrate problem. The main thing is that even the gas, if it doesn't have any water at the inlet of the pipe, it will gradually, when the temperature is reduced, it will gradually start to condense water from the gas. Yeah? And that can be enough to cause hydrate formation and plugging. So to determine hydrate formation conditions, we have laboratory tests, we have some empirical correlations, okay, depending on at which level of field development we are. If we have some samples, we can make a laboratory test. We can use a thermodynamic simulator like HYSYS, PVT-SIM, UNISIM, okay, to try to predict the hydrate equilibrium line and how it is affected by inhibitor. Okay? And then you need also tools to be able to determine the pressure and temperature evolution along the pipe. Okay, and for that we use typically a multi-phase simulator like Olga or LEDAFlow, or we could also use CFD, for example, for equipment, for manifolds, for bigger equipment that we don't know exactly how they're going to cool down for with a shutdown, okay, and how the MEG will be distributed. These simulations we have to make for many. Remember, the rate and pressure is changing with the life of the field, so you have to repeat for many conditions along the life of the field. Okay, wax, we already said. The crude oil has these waxy components and they start to form at a temperature, basically when I reduce the temperature, and I need to have this DTDR, such that that's where you have the transfer of wax uh, molecules of wax components, waxy components to the wall, and they attach to the wall. Okay, they cause increased pressure drop. They reduce the cross-section area. They can cause, ultimately, if not addressed, pipe blockage, and they can change the fluid rheology, making it more difficult to flow, and even they can have gelling, which is this problem that you have to you have to exert certain stress on the fluid for them to start moving. Okay, and sometimes gelling, this initial pressure that I have to apply has to be extremely big and simply sits stuck. Okay, one also consequence is that you create this layer on the wall, but that acts as an insulation with heat transfer. So essentially, when you have a thicker wax layer, then you're start to lose less heat to the environment. So it also gives you some help. Um, okay, some measures that we have peaking that we have discussed before. Essentially, we send um, uh, an element, rigid element through the pipe inside. We push it from one side and we receive it in the other end. Okay, and essentially this is going to scrap the wax accumulated on the wall. Another approach is avoiding that the temperature will drop significantly, so use thermal insulation, electrical heating. There are some sort of chemical inhibitor that try to again avoid that this wax will attach or will agglomerate with them. Dissolvers, after you have wax, it's trying to get this wax back into solution. Pipe coating, it's the wax attaches to the wall, so if you have some special coating that is phobic to these wax particles, then you might avoid that they will attach to the wall. And cold flow essentially, if I say that I put the fluid completely in equilibrium with the environment at the same temperature, then I won't have, even if I have wax particles out of solution in suspension, I won't have any attachment of wax to the wall. Okay, it hasn't been used. Laboratory tests, I use again the same simulators, but now they have to be transient because I want to see how the layer is going to grow and how often I have to estimate how often I have to do the pigging. Remember, pigging requires to shut down the facility production, and it requires to send this pig on the inside. Okay, and also now I might want to use CFD, computational fluid dynamics. Okay, slugging depends really on the dynamics of multiphase flow of liquid and gas, but typically is when I reduce rates. Okay, sometimes I can have slugging with high rates, but typically is when I start to reduce the rates that the regime is no longer friction dominated, but the hydrostatic component starts being significant. Okay? Also, if I have liquid accumulation on low points. Okay? I have the main problem that we discussed already is that we have fluctuating liquid and gas input to processing facilities, which can cause an issue for the operation of the separators. And in flow lines and pipeline can add vibration, also added pressure drop, so it can essentially, we will be able to produce less if we have this slugging, and also can cause fatigue in mechanical components. Okay. Some things, if the slug size is small, that I can capture with the separator size, I can change the separator size. I can also decrease, for example, the diameter of the pipeline to increase the friction component and stabilize the slugs. I can maintain the flow above the minimum flow rate. That's what is being done in Osgard with the compressor. Gas lift in the riser base. Okay, essentially I inject gas on the riser base on the example that I showed you before. Okay, I inject gas at this point to ensure that it will flow uh, in a steady state condition. Choking topside sometimes helps, but remember choking creates an extra pressure drop and then I'm losing production. Pipeline rerouting, that's something that is typically done. I try to find a configuration that won't, if there is any configuration that won't cause slugs. Also, if I do subsea separation might help, but remember always after the separator the pressure will go down so more gas will come out of solution. Okay, so it can help slugging, but you always have gas and liquid in the. For that, trust very much on a transient multiphase flow simulator like Olga and Leda to try to predict how, when, and for which conditions I'm going to have slug. I also do structural analysis using FEA, stands for finite element analysis, okay, where I try to analyze the structure, the fatigue, the vibration, okay, and I can do also laboratory experiments if I don't trust or if the conditions of slugging are if I have big uncertainty on the model, that the model is not performing well. Then we have scaling, that as I mentioned before is the change of solubility of these components in the fluid. Okay. Okay, and remember it's water, which is a problem. They're caused because of these components on the water, and they can be by changes in pressure and temperature, changes in pH, mixing incompatible water, if I have CO2 injection, and on top of it, the scaling, the crystals, they attach to where I have irregularities. Okay, like when I have grooves for a subsea safety valve, subsurface safety valve, they are typically attached to it. They cause reduction of cross-section area, pipe blockage, but more importantly, malfunction of valves and equipment. Like the subsurface safety valve, that's something that is typically affected. Okay, some measures that I inject chemical inhibitor, something that avoids the formation of these compounds. Okay, some components that avoid the formation of these salts. I can do dilution by adding more water. I can, once I have scale, I can remove its at least one of them, one type, I can remove it by injecting chemicals. Okay, I can also do mechanical removal, or I can use coating to impede or delay the attachment process to the wall. Okay, typically I have laboratory tests, simulation tools, and here on this page we have erosion, that sand production, high flow velocities, and can also be sometimes due to liquid droplet in the gas. Okay, and gas droplets in the liquid, not very common, but it can be, for example, for some machinery, some components can be liquid droplets in the gas, and they cause structural damage, vibration, leaks, and they can also lead to corrosion. You have a mechanism that can be erosion corrosion. The erosion takes out material, and then you have corrosion acting on the surface. Some measures I have to have. I have to change the geometry just to reduce the flow velocities, okay, that I have. That means either by changing the routing of the fluid, how the fluid is flowing through the structure, or changing the size, maybe making it bigger, which can increase cost. If there is some component I know I will have to change often, then to make a schedule for replacement and maintenance of component, I can reduce the flow rate, which this has two effects. One of them is reduces the high flow velocities on the component, and the second effect is that you can produce less sand because the formation drawdown becomes also less. Sand separation has been used, subsea has been used some places, and also coatings somehow. Some coatings have some resistance to, to erosion. Tools that I have available, standards like the DNV recommended practice 050501 that talks about erosion. You can use computational CFD. CFD, remember, it can also be done for 1D analysis, but essentially it's for 2D and 3D, where I try to model the flow inside some component. I do it inside a pipe, I do it inside a valve, inside a pump, and I can do some laboratory testing on some components to see what is their durability to erosion. Okay, corrosion causes the presence of water, oxygen. I have CO2 and H2S can also affect corrosion, can essentially cause leaks and integrity problems. The pressure won't be able to maintain the pipe, for example, the pressure rating that had originally. Some here I'm missing one, but it's essentially injecting chemicals to avoid corrosion. Yeah, I will show you later. Coatings. I can select material that can be done for some components, some rust resistant materials, but essentially for big transportation pipes, usually that's usually too expensive. And then I have surface passivation, in which I create another layer of some oxide that avoids corrosion to happen. Okay, I create a layer of oxide that stops reacting with the environment, and then it protects from corrosion. Hmm. Laboratory testing, uh, then emulsion. We said how it can be done, what can cause. Okay, and here essentially injection of demulsifiers. I have some agents that they help, they are going to the interface and they're helping in improving the separator by acting against the effect of emulsifiers. Okay, that like asphaltenes is a emulsifier, and they also can have heating. Okay, because heating affects the properties, viscosities, interfacial tension of the fluids, and then it can improve separation. Okay, and for that I have to make laboratory tests, and I have to use multi-phase models to predict the delta P along the pipe. Asphaltenes, um, They cause also loss of equipment functionality. If it starts to accumulate on a separator, then the separator will have less space to handle the liquid, to separate the liquid and the gas. Okay, but it can also cause the asphaltenes. They um, locate on the interface, so they can cause issues in the interface, for example, of liquid-liquid or liquid-gas. So it can lead to emulsification and foamification. Asphaltenes, they have chemical injection, mechanical removal, but there is not really a good measure that works against asphaltenes, and I have to do laboratory tests or some other simulation tools. Okay, so more broadly, to try to summarize that table I have described before, one of the main remedies for all of this problem is simply some chemical injection. Okay, simply I give something, either an inhibitor that is supposed to avoid the occurrence of this problem. Other thing is how they affect my system design and, for example, pipe and component insulation, if I need insulation or not for the temperature not to drop excessively and then have wax or hydrate or other problems. Heat tracing, in which I heat also the pipe. I wrap electrical resistance around the pipe, and then I um, try to give energy to the fluid to compensate what is losing. Lead legs, we're going to talk about it, what is a dead leg later. Pipeline routing that we mentioned for slugging, for example, we might have to take a longer route, but then we have less lower points where the liquid can accumulate, and then it can prevent the creation of slugs. Okay, well intervention, if I know there is something I have to clean often, like scale, or I have asphaltenes, or I have wax, then I have to plan how often I have to do that, to go inside the well and clean. Water injection strategy also, if I'm going to, what I told you, the mixture of, for scaling, the mixture of water between water, seawater and formation water can cause scale, so then I will have to add chemicals. And also I have to define procedures when shutting down and starting up. Essentially, if I'm going to need to inject an inhibitor, for example, for hydrate reasons, and ensure the proper distribution of these chemicals. Here is an example of that's from the PDO of Erosion, yeah, and it's giving you an overview of different chemicals. So these chemicals A and B, is this scale inhibitor A and B, two different types. Okay, I add one to the seawater and I add one to the produced water. Okay. So this probably is for injection, and this one is probably used for, because I can also have scaling in the water processing facilities topside. Okay, and you see the how often, it says continuously, because I simply don't want to deal with scale at all. Corrosion inhibitor that goes on the water, that's where I have corrosion continuously. Okay. Emulsion breaker, okay, this is the demulsifier, uh, is continuous on demand, okay, which is a bit strange, that I add to the oil and the water, total liquid. Okay. Foam breaker, that I do it when it's needed. Okay, when I start to have foam, then they inject this the flocculant wax inhibitor that I do also on a needed basis. For example, probably when it becomes cold. Biocide, also continuously. Oxygen removal, that's also for corrosion. H2S is not remover but is scavenger. Okay, oxygen scavenger and H2S scavenger, they is on the produced water. And MEG, I do it a batch and I inject it on the well stream and then do it as required. And this has required because this Ivarosen is wells that are platform wells. Okay, you don't have much subsea here in this field. Okay. Then we mentioned that we are injecting a lot of chemicals on the production stream. Okay, and then we have to say exactly what these chemicals for. If it's for disposal, for example, if the chemical is in the water, it will end up probably in the sea. Okay, so I have to be careful that the chemicals that I'm using, uh, they are not damaging to the environment and to life. Okay, so you have different categories according to, I forgot exactly what OSPAR means, but it's Commission for Ocean Safety and something. Okay, but it's a you have different categories. Green, that um, it says here substances that cause use and discharge offshore, which are considered to pose little or no risk to the environment. Okay, or have negative environmental effect. Uh, and this, for example, the MEG is in this category. The MEG is something that I can release without any problem. The main problem with MEG is that it's costly, and I have to inject a lot of it. Okay, then I have yellow, in which I have inorganic chemicals that have low that have low poisoning, and that they are break on 60% within 28 days. Okay, and then you have some other categories. Then you have red, which they they degrade slower in the marine environment, and they can accumulate and are extremely poisonous. Okay, are environmentally dangerous, and they have to be changed with environmentally friendly alternatives. Okay, black is the worst, that don't degrade, they can accumulate, they are very, very poisonous. Mm. So see here some classifications of the different chemicals we use. Like for example, the scale inhibitor is yellow, okay, and it's something that we put on the water, okay, and it will be on the water, okay, and it says that it can be moderate biodegradable or no biodegradable, okay, but it's not poisonous, and it's not going to accumulate in the food chain, okay. Emulsion breaker, these all of these are red, okay, and this emulsion breaker is dissolving the oil, and it's going to be mainly in the oil, so it won't end up in the environment in this case. At least will 5% will be on the water. Okay, wax inhibitor, again oil will be in the oil, I will be completely in the oil. Foam breaker that you have is in the oil, it will be in the oil, it may be some concentrations in the water. Flocculant biocide, that will be in the water, and that will be on the injection water or the produced water, and they are classified yellow because of they are poisonous. Okay, they are not biodegradable, and they are not going to accumulate in the food chain. Okay, if you want to know more about production chemicals, I suggest you to get this book. Very good. I think he's a professor from University of Bergen or Stavanger, if I'm not mistaken. Okay, but there you have more information on our course. I just want to make you aware of these issues, but you're not going to become experts in chemicals. Okay. So some tasks that we do during field development, during the early phase, DG0 to DG2, I simply have to detect potential showstoppers, okay, and communicate technical constraints or repercussions to the field planner. Okay, if I'm going to have slugs, if I'm going to have hydrate, I will have to inject methanol. If maybe it's a waxy crude, that can cause a lot of issues. And I have to run laboratory tests with the few samples that have been made. Later in the process, when I already have a concept and I'm preparing that concept, I'm preparing the feed, Then I have to refine the flow assurance strategy. I have to do even more laboratory tests. I have to define a management plan, what actions I'm going to take for each, prediction of pressure and temperature along my components, a study of startup and shutdown, system design and verification, and also this flow-induced vibration. Okay, so this is a comment about how do we get our chemicals subsea. So if we make, let's say we have our manifold, right? We are going to take a case for satellite wells. Okay, remember I either use a jumper or I use a flow line. Okay, and here I had essentially have one manifold, then I have other manifold. Okay. Typically or essentially maybe inside the well, okay, when the temperature, when you shut in the well, maybe the temperature will still be enough that it will be above the, for example, the most important is hydrate, okay, that is going to block completely the pipe. All others, they wax, for example, you can have some wax accumulated, but it's not going to plug completely the pipe, okay. And usually when I start producing again, that the temperature is increased, they are going to be dissolved again. Okay, but with the hydrate, for example, is very special. So let's say I have here these two. Let's put two more wells. Okay, so I have to reach these wells, and I do that with, change the color. Okay, I use the what we call an umbilical. Okay, we're going to call later, but this is an umbilical. Okay, it's a collection of pipes that I wrap around a flexible cover. Okay, and then I send it to a unit that is called a SDU. Typically has this name, subsea distribution unit. Okay, and then here I provide to each well, I provide the chemicals that they need. Okay, and I provide other things. I also provide, maybe they need power, they need the signals for the instrumentation, but I also give the chemicals. Okay, like in this case, this was a bit cut, this figure, but essentially you see here you have the umbilicals. Okay, you have here you have every well, okay, or every cluster of wells that each one of them has their own riser, okay, going to this platform is called Newark. But you have here on the other side, you have the umbilical, okay, which is here, and is going into this SDU, okay, which is here. And then this SDU is giving the chemicals and giving also other things that each one of these wells needs. Okay, that's how it looks like, the SDU. And you have okay, so you'll see for each well they have 1 2 3 4 5 6. Okay, it seems that they have 6 wells, okay, on each side. But essentially what you have, if you receive this umbilical, okay, that has all of these things, a scale inhibitor, has hydrate inhibitor, has biocide, corrosion, wax, okay, communication, power, hydraulic. Okay, remember this, we need, typically we activate valves. Remember the Christmas tree has quite a few valves, has the wing valve, the swap valve, has the master valve. Okay, all of these valves are operated with hydraulic lines, okay, with oil basically. Okay, then it goes into a manifold inside, and from that manifold you distribute to each one of the wells. Okay, well 1, well 2, well 3, well 4. And you have a valve. I think these valves that are here are these on and off valves that you have. Okay, simply a manifold. That's a cross section of the umbilical. Okay, that have what I told you, a cover, flexible cover made of strings of metal. Then you might have a high voltage cable, in this case fiber optic for the instrumentation. You have lines for, and this big line usually is for MEG injection, is the biggest, and then you have other chemicals that are typically they are sent together, okay, or either they are sent in batches if the injection is um, occasional, or they are sent mixed together if their injection is continuous. Okay, and this super duplex is simply the material is used for. Okay, you have here a more prettier drawing of how it looks like. So you have the top side where you send this umbilical, this collection of pipes. Okay, and then you enter into this subsea distribution unit. Okay, and from there you distribute to each one of the wells. That's exactly what you have in your. Okay, and I think here you can see all the different hoses with all the different chemicals you have for each well. Now, for template wells, the system is slightly different. Remember, these satellite wells, it's not the most preferred if in the Norwegian continental shelf, at least. You use these template wells. So in template wells, you remember the manifold, okay? That the manifold had a few other things that we didn't discuss that much. We had the connection for each well, then we had the two routing valves, we have the two manifolds, and then we have the pigging valve, then we have these hips, okay, but we didn't discuss the rest. Now the rest is essentially all of these hydraulic lines, chemical injection lines, communication lines, okay. So on this side, on the left, you have the connection to the umbilical, is receiving that, and then is splitting to each, okay, and all of these valves, they are to split if I have chemicals to be able to send one or to one well or the other, okay. You see here the connector that goes to the well. There are sometimes things that I have to inject on the well, okay, or at least on the wellhead, okay, at least on the Christmas tree. So then I have these connectors are typically used in this case, which is like a multi-bore connector. I have one connection which is for the main production fluid, and I have some other connectors that are, for example, communication. I have fluids, okay, for example, MEG inhibitor, okay, and they have some guides to uh, be oriented in the proper way. Okay, so it's a multi-bore connector. Let me just write it here, multi-bore connector. That's more in detail how it looks like on the Christmas tree itself. Here I have this multi-bore connector. That's how I multi-bore connector. Okay, then I have each, they connect separately. They don't, it's not allowed that this fluid will enter into that line. Okay, that's not allowed. Okay, and then you connect, that's the annular line, access to the annulus. I have here, this is the MEG control valve, okay, which is simply essentially like a choke that I can, if I need to have more MEG, I open the choke. If I need to have less MEG, I close the choke. And this is the MEG injection valve. Okay, here we have again another multi-bore connector, and I inject back here. Just a few things. Just here we have our well. Here we have our wellhead. Essentially, it's not the wellhead, but the tubing hanger. Okay. Then we have this subsurface safety valve. Okay. Subsea. No, it's I don't remember the acronym. Okay. But then you go up, you have the production master valve, you have temperature transducer, pressure transducer, you have a crossover valve between the annular, okay, and the tubing. Then you have here the scale inhibitor, scale injection valve, scale inhibitor control valve. Okay, in this case they decided it was enough because when I shut in the well, when I shut in this production master valve, this will still be uh, hot. Okay, and the scale inhibitor, Probably also I won't have any scaling inside the well for some reason. Okay, production wing valve. Uh, okay, then I have sand detector, multi-phase flow meter, production control, production choke valve. Okay, and I have along the way I have a lot of transducers. You can find this drawing in my compendium. Okay, and one thing that some chemicals they have to be injected in the well. Okay, for example, corrosion inhibitor, scale inhibitor. You also the demulsifier. So you have, let's say, the production casing. Can you have my formation someplace here? Remember, I might have concrete, the cement. Okay, and I have my tubing. Okay, that's a tubing hanger. And then what you need to have okay, these penetrators, okay, like the annular valve. Okay, the annular valve the annular valve that I show here, simply you have a piece of pipe that will be open, and here you have this valve, that's the annular master valve. Okay, that's simply the way it looks like. But when you're injecting a, for example, let's say a demulsifier or scale inhibitor, so you have to pass it through the tubing hanger, and then you have to prolong with a capillary line. It's almost a very thin hydraulic line, and you're going to inject it where you need it. Okay, usually if it's a demulsifier scaling, you want to inject it almost at the bottom of the well. Okay, so that will be, this is what we call, this part is the penetrator. This is a capillary line. Okay, and this has some other names, but they call it the mandrel. It's called an injection mandrel. Okay, so depending how many things I have to inject, either I use the same line, or if they are not compatible with each other, that's something also very important with the selection of the chemicals. If they are compatible, I can send them on the same line, all mixed, but if they're not compatible, they can cause issues, then I have to create a different line. Okay, let's say, for example, scale. Okay, dead legs, we talk about it, is when we have regular production. For example, we have this header, right? And we have different wells producing that header. Uh, if, for example, here I'm producing just from one well, here I have this routing valve, okay? But all of that, so the fluid will go from here and will follow to the left, because that's the part that is open to the process. But all the rest, here you have this crossover pigging valve, it will be simply with stagnated fluid. Okay, and this part will get some heating from the fluid flowing on this direction, but it will get cold, much colder than the rest of the fluid. So if there we have an issue where we might have hydrate, we might have some flow assurance problem, then I have to analyze the flow on that dead leg, and I have to see how I can improve it, or at least to keep it warm. Okay, I can analyze to reduce the size. In this paper, I took this from a paper that essentially they try to induce a vortex that is simply going inside the dead leg and is actually heating the dead leg. Okay, from this paper. Like in this case, that's the dead leg. We are saying fluid is entering through here, and then the dead leg will be from here all the way to here, and even further. Okay, so dead legs I have to be careful. So now just to finalize our lecture, just want here to summarize some tools that are important for the analysis. And one of them is the laboratory test of fluids, essentially hydrate, wax, asphaltenes, scale, emulsion. Um, okay, it's fluid to know my fluids, make, for example, injection water, seawater, production water to see what is the composition of that water and what kind of problems I could encounter. Then it's very important to use steady state flow simulators, essentially for pressure and temperature drop in pipe, but also in the process. And for that, I can use HYSYS, GAP, PipeSim, Olga, LEDA Flow Manager, which is a software by FMC. Uh, Transient flow simulators, they are used for example, slugging, for shutdown, shut-in, and startup. And if I have slugging, I need to have a transient simulator. Some names are Olga, which is a Schlumberger product, LEDA Flow, which is from Kongsberg, Norwegian company, Flow Manager from FMC, and HYSYS from Aspentech, which is, I think, Canadian company. You need to have thermodynamic or PVT simulators, okay, essentially to predict that equilibrium, and you use the lab results to build your model, to quality control your model. And then after you have your simulator and you have a model that you can trust, you use that for to evaluate the effect of different things. Okay, very important, you use standards. Most of the standards, they give you some guidelines, what things you have to take into account when designing a system, like DNV or API. You can use CFD, computational fluid dynamics simulation, for 3D flow analysis of pressure and temperature and flow. For that, COMSOL, ANSYS, OpenFOAM, there are a few more. And FEA, finite element analysis, to structural analysis of stresses, movement, fatigue, for example, in solids, and also heat transfer in solids. Keep. So thank you for staying until now, and that's the end of the lecture. Bye bye.